everyone, my name is Nana and I'm from the Bodhi Academy. So today we'll continue with the next part of the chapter, that is coordination compounds. Now today we'll see about the nomenclature of coordination compound, how to name the coordination compounds. The nomenclature is important in coordination chemistry because of the need to have a unambiguous method of describing formulas and writing systematic names, particularly when dealing with the isomers. So why nomenclature is important for coordination compounds is basically because there are a lot of isomers. Isomers means they have similar empirical formulas but they differ in their chemical properties. So it is better to name each and every coordination compounds to understand their properties better. Now the formulas and names adopted for coordination entities are based on the recommendation of IUPAC, that is International Union of Pure and Applied Chemistry. Now formulas of molecular mononuclear coordination entities. Now the formula of compound is short-hand tool used to provide basic information about the constitution of compound in a concise and convenient manner. Now these formulas are very important as it gives you a short and a tool which is used for the basic information, like what are the atoms or what are the elements that are present in that molecule, in that compound, and in what quantity they are present. By knowing the formula we can also tell their geometry, shape, arrangement, right? So it gives you basic information and it is a concise and a convenient manner to write the formulas also. Now, mononuclear coordination entities contain a single central metal atom. Now the following rules are applied while writing the formulas. The mononuclear coordination compound means it will only contain one central metal atom. Now what are the rules that are applied for writing the formulas? First one is the central atom is listed first. So whenever you write a formula for coordination compounds or coordination entities, the first is the central atom. You have to list the central atom first. Second, the ligands are then listed in alphabetical order. So once you list the central atom, okay, if you have cobalt, nickel, copper, iron, any of this, first mention the central atom. After mentioning the central atom, then ligands are listed. Okay, now ligands are listed in their alphabetical order, okay, which according to the alphabetical order, which alphabet comes first is then written. Now the placement of a ligand in the list does not depend on its charge. Okay, so ligand, when you place it on the list, it doesn't depend on the charge, we solely arrange it on the alphabetical order. Now polydentate ligand are also listed alphabetically. So when there are many ligands, that is polydentate ligands, we also list them in an alphabetical order. Means polydentate means what? There are different molecules or different binding sites in one molecule. For example, EDTA, right? EDTA is a hexadentate, which means it has 6 sites which can bind to the central metal atom, right? Now, these 6 sites are also arranged in an alphabetical order. Now, in case of abbreviated ligand, the first letter of the abbreviation is used to determine the position of the ligand in the alphabetical order. Now, abbreviated ligand means when we have ethene 1,2 dimer, right? Diamine. When we have En, that is here ethane 1,2 diamine. Okay, this is a bidentate, right? But we write it in an abbreviated form, that is En. Ethene 1,2 diamine, we represent it in an En form, that is an abbreviated form. Now this abbreviated form also we consider the first letter as to arrange the ligands in an alphabetical order. Okay. Now the formula for the entire coordination entity, whether charged or not, is enclosed in a square brackets. As you know, whether it is charged or not, the entire coordination formula is written inside a square bracket. This is a coordination sphere, right? Now, when ligands are polyatomic, their formulas are enclosed in parentheses. Now, ligands abbreviations are also enclosed in parentheses. So, this is a parenthesis. We have another one inside. Okay. There should be no space between the ligands and the metal within the coordination sphere. So, whenever you write, there should not be any space between the ligands and the coordination sphere. Now, when the formula of a charged coordination entity is to be written, without that of the counter ion, the charge is indicated outside the square bracket as right subscript with the number before the sign. For example, here. So, whenever, if you are not mentioning the counter ion, for example, on top we have seen COCl3 NH3 thrice and then a Cl outside, right? So this is a counter ion, I said. If you don't want to show the counter ion, we show it in form of sign, and this sign should be shown outside the coordination sphere like this. Now the charge of the cations is balanced by the charge of anions. So whenever there is charge, you have to balance the charge by the opposite one. If cation is there, then it is balanced by the anions, and if anions are there, then it is balanced by the cations. Now, naming of these are the rules. We write the formula. Now, how we will name the molecular mononuclear coordination compound? This is how we will write the formula. But how we will name them? So the name of coordination compounds are derived by following the principles of additive nomenclature. Thus, the groups that surround the central atom must be identified in the name. Okay. Now, they are listed as prefixes to the name of the central atom along with any appropriate multipliers. The following rules are used when naming coordination compounds. Now, let's see the rules which are used for naming coordination compounds. First one, the cation is named first in both positively and negatively charged coordination entities. So whenever there is a coordination entity, first you have to name the cations. Whether it has a positive or negative charge, you have to name the cation first. Now, second, the ligands are named in an alphabetical order before the name of the central metal atom or ion. So first you have to write the name of ligands in alphabetical order. Okay, according to alphabetical order, which ligand is first, you have to write the name of that ligand. After that, the central metal atom or ion ka name will come. This procedure is reversed from writing formula. Writing, first you have to write the central metal atom, then the ligands, right? But for naming, you have to write the ligands first and then the central metal atom or ion. So it is a reverse procedure from writing the formula. Now, names of the anionic ligands end in O. So the names of anionic ligands, whichever anionic ligand is there, their names will end in an O. Those of neutral and cationic ligands are the same except aqua for water, amine for NH3, carbonyl for CO, and nitrosyl for NO. So except these molecules, all the neutral and cationic ligands, their name will remain the same. So what is this? The name of anionic ligands will always end in a O. Okay. So if it is a chlorine is an anionic ligand, right? Cl is an anion, which is minus sign. So the name of chlorine will always end in an O, that is chlorido. Okay. Like this, all the anions will end in an O. Whereas for neutral and cationic ions, they will remain same, except there are few exceptions. Okay, neutral and cationic ligands, their name will remain same except for these molecules, that are for water it will be aqua, for NH3 it will be amine, for CO it will be carbonyl, and for NO it will be nitrosyl. So for these molecules, except these molecules, all the neutral and cationic ligands will remain same with their name. Now writing the formula of coordination entity, these are enclosed in brackets. Okay. Again, they are enclosed in brackets. Now prefixes like mono, di, tri, etc. are used to indicate the number of individual ligands in the coordination entity. Now why we use mono, di or tri? Just to represent the number of ligands present in the coordination entity. If you have 3 chlorine, then it will be trichlorido. Okay, if you have 5H2, it will be pentaaqua. Okay, that means 5 water molecules. Okay, so mono, di, tri we use as a prefix to represent or indicate the number of individual ligands in the coordination entity. Now, when the names of ligands include the numerical prefix, then the terms bis, tris, tetrakis are used, the ligands to which they refer being placed in the parenthesis. So, when the ligand itself include a numerical prefix, okay, at that time we use bis, tris or tetrakis as a way to refer the number. This is a molecule here, that is NiCl2 PPH3 twice. So here you can see there is a number both sides. No, so how we will name this molecule? So first, what we have to write? First we have to write the anion. Okay, that is dichlorido. Then this one, alphabetical order we have to write. No, according to alphabetical order, who comes first? C comes first, then P, right? So in alphabetical order we will write the chlorine first. Okay, so since it is an anion, it will end with O, so it is dichlorido. Now why we use bis? Because there is already a 3 here and a 2 here, right? There is already a 3 here and a 2 here. So since the ligand itself has a numerical value associated to it, so we will write it with bis triphenylphosphine nickel 2. This is the oxidation state of the metal atom. Okay. Now, oxidation state of the metal and cation, anion or neutral coordination entity is indicated by Roman numerical in parenthesis. Okay. Now these brackets are known as parenthesis. Oxidation state, as I told you, we represent it in the form of a Roman numerical in a parenthesis, that is in a bracket. Now if the complex ion is cation, the metal is named as the element. For example, CO in a complex cation is called cobalt. So if the complex contains a cation, okay, we name the central metal atom as it is. That is, if it is a cobalt, then we will name it as cobalt. If it is nickel, we will name it as nickel. If it is a iron, we will name it as iron. Okay, so we will name it as it is. Now, if the complex ion is an anion, if it is cation, we know we will name it as it is. What if it is an anion? So the name of the metal ends with the suffix ate. That means the name will end with the 3 letters, that is ATE. For example, if in same case for cation, cobalt will remain cobalt. What if the cation is present in an anionic compound? Then the cobalt will be written as cobaltate. For example, some metals, the Latin names are used in the complex ions, that is ferrate for Fe. Okay. Now the neutral complex molecules is named similar to that of the complex cation. So neutral complexes are named similar to the complex cations. How cations are named, similarly neutral molecules are also named. Now following are the examples illustrated the nomenclature of coordination compounds. So these are some examples and the explanation how their names are given. Now first one is CrNH3 thrice H2O thrice Cl3. Okay, now how this is named? It is named as according to the nomenclature. First it is named as triamine. Okay, why amine is named first? AM and AQ. Since both are A, that is amine and aqua, we will go for the second alphabet to check who will come first. So according to that, amine will come first. So it is triamine. Okay, triaqua. Since these are positive, it is chromium 3 chloride. Why 3 chloride? Because oxidation state is 3 for chromium. So it is triamine triaqua chromium 3 chloride. Now explanation to this, the complex ion is inside the square bracket, which is a cation. So this is the one which is inside the square bracket is a cation. Now the amine ligand are named before the aqua according to alphabetical order. As I told you, amines are written before aqua because of the alphabetical order. Since there are 3 chlorine ions in the compound, the charge on the complex ion is +3. Okay, since the compound is electrically neutral, from the charge on the complex ion and the charge on the ligands, we can calculate the oxidation number of the metal. Okay, from the charge on the complex ion and the charge on the ligands, we can calculate the oxidation number. In this example, all the ligands are neutral molecules. Therefore, the oxidation number of chromium must be the same as the charge of the complex ion, that is +3. So that's why the name is given like that. Now, these are again some of the examples which you can go through. Now next is the isomerism in coordination compounds. Now what are the isomerism seen in coordination compounds? Isomers are the 2 or more compounds that have same chemical formula but different arrangement of atoms. So as I told you, isomers, they are 2 or more compounds which have same or identical chemical formula but they differ in their arrangement and properties. Okay, because of the different arrangement of atoms, they differ in one or more physical or chemical properties, as I told you. So what are isomers? Isomers are the compounds with same chemical formula but different arrangement of atoms and different physical or chemical properties. Now, 2 principal types of isomerisms are known among the coordination compounds, each of which can further be subdivided. So there are basically 2 principal isomerisms. Under that there are various other isomerisms. Now which are the 2 principal types? First one is stereoisomerism and second one is structural isomerism. Okay, so stereoisomerism and structural isomerism, these are both principal types of isomerism and which are further subdivided. Now stereoisomerism is subdivided into 2, geometrical isomerism and optical isomerism, whereas structural isomerism is subdivided into 4, linkage, coordination, ionization and solvate isomerisms. Now let's first start with stereoisomers. Now stereoisomers have the same chemical formula and chemical bonds but they have different spatial arrangements. Now what are stereoisomers? They have same chemical formula, chemical bond, same chemical formula and chemical bonds but they differ in the spatial arrangement. So their arrangement differs since they have same chemical formula and chemical bonds but they differ in their arrangement. Structural isomerism have different bonds. Okay, structural isomerism means they have different bonds. A detailed account of these isomers are given below. So let's first start with the geometrical isomerism, which is the sub part of stereoisomerism. Now, geometrical isomerism, this type of isomerism arises in heteroleptic complexes due to different possible geometry arrangement of ligands. Now what are heteroleptic complexes? Heteroleptic complexes means they have 2 or more or 1 or more types of ligands associated to them, right? So important example of this behavior are found with coordination numbers. Since there are 2 or more types of ligands attached to them, there can be various arrangements, right? This gives rise to geometric isomerism. Now in a square planar complex of the formula, that is mx2l2. Okay, so these are two different types of ligands which are attached to the metal atom. Now the two ligand X may be arranged adjacent to each other in a cis form or known as cis isomerism. So if this is the central metal atom, if both the elements XX and LL both are placed adjacent to each other, this isomer is known as cis isomer. If they are in the opposite form, that is MX, X, L and L. So both of them are arranged opposite to each other. This is known as trans isomer. Okay, so there is cis and trans isomer, which is depicted here. This is cis and this is trans. Okay, cis means both are on one side, trans means both are opposite to each other. Now, other square planar complex of the type MAXBL, MABXL, where A, B, X, L are unidentates. Okay, show three isomers, 2 cis and 1 trans. Okay, so here again you can see cis and trans, both of them are together, this is cis, both of them are opposite to each other, this is trans. Okay, now you may accept to draw this structure, attempt to draw this structure. Such isomers is not possible for tetrahedral geometry. So this isomerism is not possible for tetrahedral geometry, but similar behavior is possible in octahedral complexes. So cis and trans or geometric isomerism is seen in square planar and octahedral structures. Okay, in which the two ligands X may be oriented in cis or trans to each other. Now this is now this type of isomerism also arises when dientate ligands are there. So if there are dientate ligands, then also there is an cis and trans arrangement that is seen. So this is an dientate ligand. So you can see this is trans and this is cis. Here also you can get a cis and trans arrangements. Now another type of geometrical isomerism occurs in octahedral coordination entity of the type that is Ma3B3, like CONH3 thrice, NO2 thrice, means two different molecules. This is amine and this is nitrite. Both of them are present in tri form. Okay, if three donor atoms of the same ligands occupy adjacent position at the corner of the octahedral face, we have the facial or FAC isomer. When the positions are around the meridian of the octahedron, we get a meridional or mer isomer. When we have this type of coordination where there is 3 ammonia and 3 nitrite. If all the 3 nitrite and ammonia are present adjacent to each other like this, all the ammonia and all the nitrate, they are present opposite to, or they are present together in one face. This is known as facial isomer or FAC isomer. If when their position change to a meridian order, means two are opposite and there is this which are opposite to each other in this form, okay, then it is known as meridional or mer isomer. Okay, so we have seen cis, trans, facial and meridional isomers which are related to geometrical isomers. Now next is the optical isomerism. Now optical isomers are minor or mirror images that cannot be superimposed on one another. So they are mirror images, okay, but they cannot be superimposed, they cannot be imposed on one another. Okay, now these are called enantiomers. Okay, optical isomers are mirror images that cannot be superimposed on one another. When they cannot be superimposed on one another, these are called enantiomers. Now the molecules or ions that cannot be superimposed are called chiral. Okay, since they are called enantiomers, they are also known as chiral. Now the two forms are called dextro and levo. Okay, so dextro means it rotates in a right hand side, levo means it rotates in a left hand side. So there is a dextro and levo molecules. Now depending upon the direction they rotate, the plane of polarized light in a polarometer. Okay, now D means it rotates to the right, so dextro means it rotates towards the light and levo means it rotates towards the left. Now, optical isomerism is common in octahedral complexes involving dientate ligand. Now optical isomers, they are common in octahedral complexes involving dientate ligands. Now in a coordination entity of the type PTCl2En twice, only the cis isomer shows an optical activity. So this is PTCl2En twice. Here only cis 1 shows an optical isomerism, whereas trans doesn't show an optical isomerism. Next is the structural isomerism. Under structural isomerism, we have linkage, coordination, ionization, and solving. So first is the linkage isomerism. Linkage isomerism arises in a coordination compound containing ambidentate ligand. What are ambidentate ligand? I have given an example of SCN and NO2, right? Where sulfur can also bind to the metal atom, nitrogen can also bind to the metal atom. Here nitrogen can also bind to the metal atom, oxygen can also bind to the metal atom. So when there are two binding spots in one ligand, it is said to be ambidentate. So anyone can bind to the metal atom. Now linkage isomerism, it arises in an ambidentate ligand only. Now a simple example is provided by the complex containing thiocyanate. As I told you, SCN is a thiocyanate, where NCS minus, which may be bind through the nitrogen to give MNCS or through sulfur giving MSCN. So you can get two, that is metal atom bound to SCN or metal atom bound to NCS. Okay. Now Jorgensen discovered such behavior in the complex. Okay, he is the one who discovered this behavior in the complex. Now, which is obtained as the red form, in which the nitrite ligand is bound through oxygen. So he found it in nitrite ligand, where it is bound through oxygen and it formed an yellow color compound in which nitrite ligand is bound through nitrogen. So there are two forms. Okay, it formed a red color thing and a yellow color thing. The red color one is formed because it was bound through oxygen, and the yellow color compound was formed because it was bound through nitrogen. So this is how he come up with the concept of ambidentate ligands and linkage isomerism. The next is the coordination isomerism. This type of isomerism arises from the interchange of ligands between cationic and anionic entities of different metal ions present in a complex. So coordination isomerism, it arises for the interchange of ligands between cationic and anionic entities, where there is an interchange between ligands. As an example is provided by CONH36 CrCN6, in which NH3 ligands are bound to CO3 plus and CN ligands are bound to Cr3 plus. Okay, in this coordination isomerism, the NH3 ligands are bound to Cr3 plus and the CNs are bound to CO3 plus. Okay, so here we can see the interchange of ligands between cationic and anionic entities. Okay, so here the ammonia can bind to chromium and CN can bind to cobalt. Okay, so either way the bond can happen. So that is a coordination isomerism. Now ionization isomerism, Means this form of isomerism arises when the counter ion in the complex salt is itself a potential ligand and can displace a ligand which can then become the counter ion. So what is ionization isomerism? When there is a counter ion present, this counter ion itself is so powerful that it can remove any one of the ligand and place itself as a counter itself as an ion. For example, here Br is more powerful than sulfate, so it can replace sulfate as a counter ion. You can see CONH35SO4 Br, but Br is stronger, so it replaces itself with SO4. It becomes CONH35 BrSO4. Okay, so this is an ionization isomerism. Next is solvate isomerism. Now what is a solvate isomerism? This form of isomerism is known as hydrate isomerism. In case where water is involved as solvent, this is similar to ionization isomerism. Solvate isomerism differ by whether or not a solvent molecule is directly bonded to the metal ion or merely present as free solvent molecules in the crystal lattice. Solvate isomerism is also known as hydrate isomerism, where water is involved in as a solvent. Okay, whenever we use water as a solvent for the formation of the coordination compound, this is similar to ionization isomerism. What is ionization isomerism? Where one removes the other and replaces itself. So similarly, hydrate isomerism or solvate isomerism, here what will replace what? The water will replace the other ligands present in that coordination compound. Okay, so solvate isomers differ whether or not a solvent molecule is directly bonded to the metal ion or merely present as free solvent molecules in the crystal lattice. Okay, it differs where if how solvate isomers differs, it differs like if the solvent is directly bonded to the metal ion or it is just merely present as a solvent molecule in the crystal lattice, not attached to the metal atoms or ions. An example is provided by the aqua complex, that is CrH2O6Cl3, which is violet, and the solvate isomer is CrH2O5Cl Cl2H2O, which is grayish green. Here you can see there are a lot of other molecules which are associated to the compound when we mix it in water. This is solvate isomerism. Now, so in our today's video we have seen about the naming, right, nomenclature of coordination compounds. We have seen how to write a formula for coordination entities, how to name the coordination compounds. We have seen one example how to name it. Then we have started with isomerism in coordination compounds, and we have seen the two principal types of isomerism, that is stereoisomerism and structural isomerism. The stereoisomerism is subdivided into geometrical and optical isomerisms, whereas structural isomerism is subdivided into linkage, coordination, ionization and solvate isomerism. And we have seen each of them in detail. Like geometric isomerism, it depends on the geometry of the molecule and gives cis, trans, fac and mer isomers, right? Then we have seen optical isomerism. Under that we have seen dextro and levo rotations. Then we have seen linkage isomerism, which is related to ambidentate ligands, where there are two sides for the molecule to bind to central metal atom. Then we have seen coordination isomerism. Now what is coordination isomerism? Cations and anions in the coordination entity can be interchanged. For example, CONH3 and CrCN. Okay, this can be interchanged. We can get COCN and CrNH3. Okay, so we can change the cationic and anionic entities in the coordination compounds. So that is coordination isomerism. Ionization isomerism is like a displacement reaction, where the counter ion which is present outside the coordination sphere can replace the ligand which is present inside the sphere if the counter ion is more stronger than the ligand. Okay, so that is ionization and isomerism. Solvate isomerism is similar to ionization isomerism because it is also known as hydride isomerism, where water can replace the ligands. Okay, so thank you for watching my video. Please do like, share and subscribe to our channel.